Rate that violates every known principle of river mechanics. No earthquake, no drought, no diversion. And yet somewhere between Caron, Illinois and the Gulf of Mexico, nearly half the river's volume is vanishing into nothing. Where is 47% of America's greatest river disappearing to? Why are Army Corps engineers staring at data that should be impossible? And what happens to 18 million people when the water they drink begins draining into the earth itself? The Mississippi River drains 41% of the continental United States. 31 states and 2 Canadian provinces feed their runoff into this single channel. According to USGS measurements, the river discharges an average of 520 cubic kilometers of water past Vicksburg each year, making it the 7th largest river system on Earth by volume. This is not merely a river, it is a continental circulatory system. For over a century, that system behaved predictably. USGS monitoring stations tracked every pulse of flow, every seasonal surge, every drought year decline. The numbers followed patterns engineers could trust. Economies rose on that predictability. But the patterns have shattered. Between Cairo and the Gulf, the mathematics of water movement have stopped making sense. Gauges upstream report normal discharge. Gauges downstream record catastrophic decline. The volume difference exceeds the entire annual flow of the Colorado River, and no one can find where the missing water has gone. The economic machine built on the Mississippi's predictable flow is staggering. According to the Bureau of Transportation Statistics, the river carries over 500 million tons of cargo annually, valued at more than $405 billion. A single 15-barge tow hauls as much grain as 870 semi-trucks. 92% of U.S. agricultural exports pass through this system. The ports of New Orleans and South Louisiana handled 20% of all American waterborne commerce. 60% of the nation's grain exports flow south on these waters toward hungry markets overseas. The river provides drinking water to 18 million Americans. It supplies cooling systems for power plants, feedstock for chemical facilities, irrigation for farms stretching across 8 states. Remove the Mississippi and you remove the arterial blood supply of an entire economy. But something has changed in the artery itself. The transformation began nearly a century ago, born from catastrophe. In 1927, the Mississippi broke free of its banks in the most devastating flood in American history. More than 27,000 square miles of land drowned beneath 30 feet of muddy water. Over 600,000 people fled their homes. The death toll reached into the hundreds. Congress responded with the Flood Control Act of 1928. For the first time, the federal government assumed total responsibility for taming the river. The Army Corps of Engineers began constructing what would become the largest system of levees on Earth. They built over 3,700 miles of embankments and floodwalls. They installed 29 locks and dams on the upper river alone. They dredged channels, erected wing dikes, and armored banks with concrete revetments. They raised the old river control structure to prevent the Mississippi from abandoning its course entirely. The engineers succeeded beyond anyone's expectations. No levee built to Mississippi River Commission standards has ever failed. Navigation became year-round reliable. Floods that once swept communities into oblivion now rarely breached the defenses. The river transformed from a wild, unpredictable force into something resembling infrastructure. But success created consequences no one anticipated. When you imprison a river between walls of earth and stone, you change the fundamental physics of how water behaves. Confined channels flow faster, faster water scours deeper, and a river denied its floodplain becomes a river starved of the sediment that once replenished its bed. The first signs of systemic failure appeared in the forecast models. At the Lower Mississippi River Forecast Center, hydrologists began noticing discrepancies that defied explanation. Water entering the system upstream was not arriving downstream in expected volumes. The shortfall was not subtle, it was massive. Month after month, the gap widened. Engineers recalibrated instruments, suspecting sensor malfunction. The sensors were accurate. They checked for unauthorized diversions, hidden tributaries, measurement errors in the network. Everything checked out. The water was simply vanishing between gauging stations. Federal agencies assembled a crisis investigation team. NOAA hydrologists, USGS geologists, Army Corps engineers, a multidisciplinary group with one mandate: find where the water is going. They examined every hypothesis systematically. The first suspect was agricultural withdrawal. The MSI Valley alluvial aquifer stretching beneath the Delta region supplies irrigation for one of the most intensively farmed landscapes in America. According to USGS data, over 12 billion gallons of water are withdrawn from this aquifer daily. But the mathematics did not support this explanation. Agricultural withdrawals have remained relatively stable for decades. The sudden accelerating loss of river volume far exceeded anything irrigation could account for. Pumping records showed no anomaly. The farms were not drinking the river dry. The investigators turned to levee seepage. Miles of earth and embankments separate the river from its former floodplain. Ground-penetrating radar surveys examined levee integrity along hundreds of miles. The levees were performing as designed. What the investigation discovered instead overturned decades of assumptions about the Mississippi's structure. Core samples extracted from beneath the riverbed revealed something engineers had never anticipated. The natural layering of sediments, the stratification that had controlled water movement for millennia, had been destroyed. Instead of distinct layers of clay, silt, and sand, each with different permeability, the samples showed a homogenized, highly permeable mass. The riverbed had transformed into something resembling a geological sponge. A healthy river channel maintains hydraulic resistance through sediment stratification. Clay layers act as barriers, preventing water from draining downward. This resistance keeps the river contained within its banks, moving horizontally toward the sea. The Mississippi had lost this resistance entirely. The cause traced back to the very engineering projects that saved so many lives. Levees prevented the river from migrating laterally, the natural behavior that once spread erosive energy across vast floodplains. Confined between fixed walls, the river's power concentrated downward. For decades, the channel scoured deeper into its own bed. Simultaneously, the dams and reservoirs upstream trapped sediment that would naturally replenish what erosion removed. According to USGS research, major Missouri River dams alone capture 100 to 150 million metric tons of sediment annually. The lower Mississippi, starved of this material, began cannibalizing its own substrate. The sediment discharge of the entire basin has declined by 60% since the era of dam construction. The river that once built Louisiana's coastal wetlands now lacks the material to maintain its own channel integrity. But bed destabilization alone could not explain the scale of water loss. The investigation uncovered a second compounding factor operating beneath the surface. The MSI Valley alluvial aquifer has been in a state of depletion for decades. Agricultural pumping has drawn down groundwater tables across thousands of square miles. In some areas, groundwater levels have dropped by dozens of feet since monitoring began. This depletion created something hydrologists call hydraulic gradient, a pressure difference between the river above and the depleted aquifer below. Water flows from high pressure to low pressure. The gradient was pulling river water downward. What emerged was unprecedented in hydrologic science: induced infiltration at continental scale. The water was no longer merely transporting water to the Gulf, it was actively recharging the depleted aquifer beneath it. The destroyed sediment layers offered no resistance. The pressure gradient provided relentless pull. The Mississippi had transformed from a transport-dominated system to an infiltration-dominated system. The water was draining into the earth. Along the river's lower reaches, the consequences became visible in human terms. In Plaquemines Parish, Louisiana, families began noticing something strange in their topwater. The taste changed, pipes corroded faster than they should, appliances failed prematurely. Salt water from the Gulf of Mexico was creeping upstream. Normally, the Mississippi's powerful downstream flow keeps the ocean at bay. But as the river's volume declined, so did its ability to resist intrusion. In 2023, the saltwater wedge advanced farther upriver than in any time in recent memory, threatening drinking water supplies for nearly 1 million people. The Army Corps of Engineers scrambled to construct underwater sills, barrier mounds designed to block the denser saltwater moving along the riverbed. The cost exceeded $20 million. The solution was temporary. One barge captain who has worked these waters for 30 years watched the river change beneath his hull. His loads grew lighter as channels shallowed. Routes that once carried fully loaded tows now required draft restrictions. In October 2022, over 2,000 barges sat stranded in backup, their progress halted by groundings on sandbars that appeared without warning. He summarized what so many river workers were thinking: the Mississippi is becoming something else. Official reports to Congress used careful language, but the conclusions were stark. The losses are unsustainable. The decline is accelerating. The system has entered a structural regime shift from which there may be no return. The ecological consequences cascaded through interconnected systems. Fish populations declined as water temperatures rose in shallowing channels. Mussel beds that once filtered millions of gallons daily died off in stretches where flow became inadequate. The Mississippi Flyway, migration corridor for hundreds of bird species, lost critical wetland habitat. Navigation failure followed ecological collapse. Channel depths that once accommodated fully loaded barges dropped below minimum requirements. In October 2023, USGS gauges at Memphis recorded water levels of -12 feet, the lowest in recorded history. Barge traffic that normally carries 65 million metric tons of grain annually fell by over 75% during the worst periods. Barge freight rates that averaged $11 to $12 per ton in normal times spiked above $70. Farmers watched their profit margins evaporate as transportation costs consumed revenue that should have reached their accounts. The economic damage rippled outward. Barge companies entered bankruptcy. Port facilities reduced operations. Grain elevators that depended on river transport lost their competitive advantage against rail alternatives. Towns built on river commerce began contemplating futures without it. The Army Corps proposed restoration measures: release more water from upstream reservoirs, reduce groundwater pumping in the delta, emergency dredging to maintain navigation channels, construct recharge basins to return water to the aquifer. Each solution encountered the same problem: the system worked against itself. Extra reservoir releases infiltrated through the permeable bed faster than they could restore downstream flow. Groundwater pumping restrictions shifted demand to surface withdrawals, pulling more water directly from the river. Recharge basins pumped water into aquifers that drained right back toward the depleted zones. The Army was attempting to fill a bathtub with a hole in the bottom. Operational costs escalated. Dredging that once maintained channels on predictable schedules became continuous emergency intervention. Sill construction became annual rather than occasional. Monitoring systems required constant expansion as new problem areas emerged. The American Geophysical Union Conference presented findings that challenged fundamental assumptions about river management. The historical behavior of the Mississippi River is no longer applicable to current conditions. This statement carried weight beyond hydrology. It meant the models used for flood prediction, navigation planning, economic forecasting, every system built on understanding how the river behaves had become unreliable guides to future conditions. The realization settling over those who understood the data was profound and disturbing. There was no single villain in this story. Each engineering project had solved a real problem. Levees prevented floods, dams controlled surges, reservoirs stored water for drought years, dredging maintained commerce. Every intervention made sense in isolation. Together, they created emergent failure. The Mississippi was not drying in any classical sense. Precipitation across the basin remained at or above historical averages. Tributaries continued feeding water into the system at expected rates. The river was not suffering from drought, it was suffering from transformation. The hydraulic gradients created by human intervention, the depleted aquifers, the destabilized bed, the confined channel, had fundamentally altered what the Mississippi River is. It had become something new, a system that drains itself. The alterations accumulated over a century cannot be reversed on any practical timescale. Floodplains disconnected by levees cannot be reconnected without destroying communities built in their place. Sediment trapped behind dams cannot be released without devastating downstream infrastructure. Aquifers depleted over decades cannot be refilled in years. The bed destabilization itself may be permanent once the stratified layers that controlled permeability are destroyed. No natural process rebuilds them on human timescales. The question haunting engineers and hydrologists is not whether the river will reach a new equilibrium. Rivers always do. The question is where that equilibrium lies, how long the transition takes, and who bears the cost. The monitoring continues. Satellites track surface changes from orbit. Gauges measure discharge at dozens of stations. Scientists publish papers quantifying decline rates. Congressional hearings receive testimony about infrastructure needs. The river keeps draining. The Mississippi carries the runoff of a continent, the commerce of a nation, and the drinking water of 18 million people. It has done so for millennia. For 100 years, engineers believed they had mastered it. What they created instead was a system optimized for human benefit in the short term and structural collapse in the long term. The river did not fail. It responded logically to the conditions imposed upon it. The success of flood control became the mechanism of hydrological failure. The pipes and levees and dams that protected so many lives altered the physics of water movement in ways that are now draining the continent's greatest river into the aquifers beneath it. Rivers are not machines. They are complex adaptive systems. They respond to change with change. The Mississippi is responding. Scientists can measure the decline. They can model the processes. They can project the trajectories. What they cannot do is stop them with the tools currently available. The forces involved, continental-scale hydraulic gradients, century-old infrastructure commitments, economic dependencies running into the hundreds of billions, exceed the capacity of any agency or budget to reverse. The monitoring stations will continue transmitting data as the numbers decline. The barges will carry lighter loads on shallower channels. The salt water will creep upstream each dry season, retreating less each time the rains return. The aquifers will continue accepting water the river cannot afford to give. And somewhere between Cairo and the Gulf, the Mississippi will continue vanishing into the earth, a river system, engineering optimized straight into a regime shift no one predicted and no one knows how to stop. What happens when the continent's circulatory system begins bleeding out? What new equilibrium awaits when the transformation is complete? And in a world where success can become failure across generational timescales, what other engineered systems are approaching thresholds we cannot see? The Mississippi keeps these answers hidden beneath its muddy surface, but the gauges are watching and the numbers keep falling. Amazing discoveries. Make sure to subscribe and hit the bell icon. Share this video with friends and join the discussion on what these findings could mean. Your thoughts and questions are important, so let's explore incredible mysteries together.